什么鬼？写不动。没什么人。同学可能先帮我把门关上。有人来。同学帮我把门关上，因为外面很吵。视窗。Okay. So any question from this time? Yeah. So brief review. This time we go over once again this is upper bound for Grover's algorithm. So we showed in quite detailed calculation how Grover's algorithm work. So basically, we have two reflections. Let's see where are the reflections. Okay, so reflection 1, reflection 2, and we have two reflections that are equal to 1 rotation, and everything happens in this 2D plane, spanned by equal superposition of all state and equal superposition of mark item. And so two reflection turn into a rotation, and the rotation angle is about square root n over m. Where we don't have theta here anyway. And so the angle is about square root n over m. Sorry, m over n. And you want to rotate from your starting state to this beta state. So you need about, where is it? Yeah, here. You need about pi over 2 divided by theta number of steps. And so total number of steps about this pi over 4 square root n over m. And if you ignore m, that's square root n, or the square root n number of rotation steps. You need to do your Grover's algorithm. Sorry. Okay. And excuse me. Let me try to resolve this. Oh. Okay. Yeah. And yeah, so that's Grover's algorithm. And then there is an issue of you are doing a rotation on this plane. So if you don't know m, then you are just going to rotate to whatever place you don't know where to stop. And so your success probability is actually be this sinusoidal. So if you want to really have this square root n over m scaling, then you need to know m. Otherwise, you need to do something smarter. And there are a lot of details around this. We'll have a better summary of this later in the course. But for now, we're assuming our algorithm knows m, and if our algorithm doesn't know m, which once again m is the number of mark item, then here we have a really sketchy proof that you can do a binary search on m. So basically, you just increase the number of iterations you run in your Grover algorithm with some exponentiating series. So like 1 over 2, 1 square root 2, square root 2 square, etc. And yeah, and then you will find your mark item or the square root n over m steps with high probability. And these don't actually give you more scaling, not even log factor. You just need the actual constant factor, which I actually write the constant wrong because So the constant, okay, let me use red. Because when you run, this is the summing over the extra things you need to do is summing over geometric series. So the number of steps you need to run is so extra factor is 1 plus 1 over square root 2 plus 1 over square root 2 square, etc. And because when you sum over geometric series, that's just a constant. So you only get this 1 over 1 minus, it should be 1 over square root 2 extra factor as your complexity. Okay? So let's go over. Then we spend a lot of time on this quite messy quantum counting thing. So the algorithm idea here is pretty simple. Or I should say quantum counting. So quantum counting is you want to estimate m, but it gets very tricky because, or the calculation get very tricky because when you estimate m, then how many query you need actually depends a lot on the precision you want on m. Okay? And here we use this notation such that we have some multiplicative error on m, so epsilon. And so if you want the additive error, delta m, then that's epsilon times m. And then, for example, if you want constant error, then you need square root m queries. And say, so you can see that in a very bad case, if like say m is, let's go back to green. So if m is about, so in a worst case, m is about order n, and and you want the constant error to be very small, smallest possible 1, right? And you want the delta m to be about 1, then you need like order n query. So you basically need to see everything. If there are a lot of mark items, then you know to know the exact number. Okay? And this is, I guess we didn't talk about this because this is consistent for, so a little digression. This is consistent for computing the parity function. This is actually very hard. Right? So parity. So if you want to know the basically the parity over m, then that's very hard. Okay? It can be proven with omega n lower bound. Okay? So if you want to know if m is an even number or odd number, that's already very hard. This is slightly easier than this counting, but anyway. So that's a little digression, and we can keep it here. Anyway, so back to quantum counting. Quantum counting is a problem of finding this m number, and we parameterize this with epsilon multiplicative error, and we show that there is an algorithm do this with 1 over epsilon square root n over m. And we should have, say here, classical. So classical, we have it down there, but it's better to have it here. So classical is this thing square. So 1 over epsilon square and over m. And I believe this is a theta. Okay, so we have a quadratic speed up for quantum here. And yeah. And the algorithm we use here is quite complicated. You use phase estimation on our global iteration because you can show that our global iteration is just a rotation on two-dimensional space, and it's not too hard to convince yourself that when you write down the unitary matrix of a rotation, then it's a rotation matrix, then it's the sine cosine thing, and you can easily calculate its eigenvalue, and it's going to be ei theta e to the I2 pi theta. So so when you do phase estimation, you will learn this theta, and we know that theta I is about square root n over n. And so we can just invert this relationship, and you will learn your m. So that's the idea. And then we run through a whole bunch of calculation to see that what's the precision of your phase estimation, and how does that relate to the precision on theta, and how precision on m. And we do this quite carefully, and in the end, and there are extra turn stuff, very annoying. Anyway, then in the end, we see that the number of, so m is the number of precision digits you have need to be about 1 over epsilon square root n over m. Sorry, 2 to the least m. So m is the number of precision bit, and 2 to the m is about 1 over epsilon square root n over m. And we know 2 to the m is about 2 to the t, which is the number of oracle codes we need to run. And it's also about the time complexity of the algorithm. And anyway, the query complexity, as we shown, is 1 over epsilon square root n over m. And if you still remember, so there is a little tricky point here. So this is a little circular logic here now, because if you want to actually have this scaling, then you also need to know m at least to pretty good precision, because, well, you need to know m to set up your algorithm with the correct. You need to know m to set up your algorithm with the correct m and correct t, correct small m and correct small n, correct small m and correct t. So yeah, but you don't know m to begin with, then things are tricky, right? So you can presumably do this with some binary search again, but we'll say later that there are better things to do. Okay. And anyway, so there are two things. So you can do this a little worse. So you can just pick m to be the worst possible, so pick m equal to 1. Then you just use all the square root and queries, and so this is what the textbook do. Okay, so this is what the book do. They say if you pick square root n, then you will get very good precision, and that basically allow you to do everything. In particular, that will allow you to do global search. So you know you don't know m, then you can at least do global search with all the square root n. Although this is worse than what we know as possible, right? Because we know we should be able to do all the square root n over m, right? So it's a little worse. You can at least do this with quantum counting. Okay, this is clean this up. Okay. So that's what book do, and there is something I can that's a little wrong. Don't know what you remember, but anyway, we say we can just look at delta theta, right? So if we want to do global search, we just need to get delta theta correct. But so actually, we want delta theta over theta to be some constant. So right, because that means each step you rotate some theta by actually rotate some delta theta plus minus theta. Sorry, some theta plus minus delta theta. And so if this is a constant, then your final angle will have a constant multiple error, right? You want your theta add up to pi over 2. Then if this is a constant fraction, then your final angle will have a constant fraction error. And so what's the condition for this to be a constant? Then, so delta theta, as we say here, is about 2 to the minus m, and we know theta is about square root n over m. So those two should be like a constant factor of each other, and you invert it, then you see that 2 to the m is about square root n over m. And yeah, so basically, this is like epsilon being constant, right? So you want, if you still remember, this is about 2 to the t if we ignore the delta factor, and 2 to the t is the number of query. So if you want this to be a constant, then the number of queries is still square root n is about square root n over n. And yeah, I guess once again, this requires you to know what's m to get this optimal. So that's quite annoying. And okay. So hopefully I have convinced, I guess, so those are mostly review. Any question about the review? No? Okay. So hopefully I have shown you enough annoying part of this textbook quantum phase estimation algorithm to justify that we want another phase estimation algorithm. Okay. So this is a quite recent result. So this is in 2019 August. So people come up with the somewhat simpler quantum counting algorithm. So there are two setting points. So we have been talking about this setting point a lot, right? So their algorithm doesn't need to know m because they are doing kind of binary search thing. And but their main motivation is they want the phase estimation algorithm. Sorry, not phase estimation. A quantum algorithm or quantum counting algorithm that doesn't use quantum Fourier transform. Because remember we were doing phase estimation. We do phase estimation, and that's why we need quantum Fourier transform. But as people are trying to build quantum computer, they find out that quantum Fourier transform is actually pretty hard to do. And quantum counting is really a Grover-based algorithm. So maybe you can just do this with Grover iteration. Then that will make the algorithm, I guess, simpler in the sense that easier to be implemented on a quantum computer. Okay? And also conceptually, this is a Grover thing, so we should really not need to do quantum Fourier transform. It's a different kind of algorithm. Okay? And yeah, so they are able to show that you can do quantum counting with mainly using Grover iterations and smarter classical post-processing. And here we say that yeah, there is a little trade-off where you need older log n, some log vector overhead in the computational complexity. I'm not sure, but I think there are follow-up, so maybe this is removed. Not quite sure. But anyway, for now, let's keep this here. Yeah. So yeah, if you're interested, you can look up this paper and see that it's actually not too hard because most of it is classical arithmetic to make sure your things are in correct place. And yeah, so that's quite interesting. And we know that you can actually do quantum counting to do what we want. Okay. So it's a little funny because you are using a much complicated tool to do a simpler thing. But remember, we motivate quantum counting by saying it can be used to do this Grover algorithm. And indeed, this new algorithm by Scott Aronson is able to do it, although it's much more complicated than just doing this binary search. So it's a bit funny. Anyway, that's possible. And so that's the end of quantum counting. And let's switch or go back a little bit to Grover search. So why do we want Grover search? It doesn't give exponential speed up, and it doesn't break a crypto system like it doesn't break a ISA. But it's actually pretty useful for at least for theorists, because search is a very general problem and you can get speed up for a level problem. So here is an application for Covert search. And it's very general. It's you are spinning up your brute force solution for NP problems. Okay? And remember, for NP problem, there is always a brute force solution because by definition of brute NP problem, there is some kind of what is this called? I guess efficient checking algorithm, where you can give a checking algorithm a witness and a state, and if your state is a yes an input and a witness, and if this input X is a yes instance, then there must exist a witness that accept. So you can just check through all possible witnesses to see whether your yes instance is yes or no. Okay, and there will be some exponential number of things you check through. Yeah. So yeah. And so where is this quantum algorithm? The quantum algorithm is that. So where the Grover constant is that you can build this checking algorithm as a quantum circuit. We didn't quite show this, but remember there is a quantum gate for Toffoli, and Toffoli is universal for classical computation. So you can do every classical circuit into quantum circuit, in particular this checking algorithm M, big M. And if you build that into a quantum circuit, and then you can also do a phase kickback to make it a phase version, right? And anyway, yeah, so you can build it into a phase version, then you will have this oracle that runs on. Sorry, it's a little complicated. So you also build in this X into this M. So I should say F sub X, right? Okay, this is kind of like F sub X, but that's a lot of X, so that's not really everywhere. And anyway, you can define this F of witness, F as a function of witness. That's just applying this checking algorithm M on W and X. And you build that into a quantum circuit and do a phase kickback, so you get this phase version of -1 to the F of W when you input this W. Okay. And so if you think about you get this kind of circuit, then you can just use it kind of black box way and run Grover algorithm. So it's not quite a black box because you know the inner working, but you can still treat it as a black box when running algorithm anyway. Just put in whatever this thing when you need a block for OF. And anyway, so you can run Grover's algorithm with this oracle, and you will find whether W exists. So this is solving the decision version of Grover. And you can find where W exists using Grover's algorithm. Okay. And so if you found the W, then you know X is a yes instance. You don't find the W, you know X is not is a no yes instance. So you solve your NP problem by doing this covert search. And so this is speed up of the brute force search algorithm, and it's only a quadratic speed up, so it's still pretty slow. In particular, so it needs this many number of calls. So where this M is the I'm making a typo here. It should be W. It should be W. And anyway, so the M here, this small m is the length of your witness. Okay? And so if you do classical search, you need to look through all 2 to the m different witnesses. But you are running Gover's algorithm, so you only need 2 to the m taking a square root, so that's 2 to the m over 2. Yeah. So there is a little speed up here. And that's the application of Gover's algorithm, a very naive application. So you can get some speed up for solving NP problem. But there is a little caveat here. So even though you can do this, it doesn't guarantee a quantum speed up for every NP complete problem. Because things are a little tricky, since the classic algorithm can be a little smarter than doing this. Okay? So for some problem, there are classic algorithms that do less than this. Say maybe they do 2 to n over 3 just because they are a little extra structure. So, and those algorithms might use something like dynamic programming, and it's not very obvious whether you can do Grover speed up on those. So yeah, it's still actually an open problem whether you can get a Grover speed up on every NP problem. Right. Yeah. So yeah. So for some NP problem, is still open that how do you get just a polynomial speed up by using Grover algorithm, combining with classic algorithm. But the classic algorithm are more complicated than just doing brute force search through all witnesses. Okay, so it's a quite interesting research area. And okay, any question? So that will be wrapping up the upper bound part of Grover's algorithm. If everyone is okay, then we are going to go into the most technical part of this course. That's the lower bound of Grover's algorithm. Okay. And obviously we don't have time to go through this everything today. So I will try to have finish a high level intuition today. We have 23 minutes. Okay. Should be okay. Okay. And hopefully people can get the idea. So we want to lower bound the query complexity of Grover's algorithm. And it's quite hard. So lower bounding everything in computer science is hard. And lower bounding the query complexity for quantum algorithm is even harder. So we didn't quite say here, we should say it here. So that's because you can query everything in superposition, right? In superposition. That's the harness in lower bounding anything in quantum. So remember, can we have it here? Pick it all up here. So our quantum workload look like this, right? So you have input register, output register. And if you have input register, you can put the equal to inside here, and we actually do that. Then your output register will kind of having information on f of x for x, right? And now that gives us trouble because, say, for classic algorithm, you might say your f is very long, and if you don't query everything, then there is some place you never see, and that place might be crucial for distinguishing things. But for quantum algorithm, you can kind of see everything at once, and how do you actually say your algorithm need to use your query many times when one query can kind of give you information on everything. So That's very hard. And there's something else I want to say. So yeah, and once again, so for lower bounding over the algorithm, uh, so sorry, so we are saying optimality for Grover's algorithm. So we are actually not lower bound for Grover algorithm. We are not saying like you run Grover algorithm and then you see that you need to actually do square root n over m to rotate to top, right? Just draw it here. If you know you are running Grover's algorithm, then it's pretty easy to see you need a square root n over m to go to this top here. But what we are lower bounding is this search problem. Okay, so we are saying actually the decision version of the search problem. So I'll say this first. So once again, the decision version of the search problem says that if you want to know output is yes and no, and yes is f of x equals 0, when yes is when your input, remember your input is this function and or this truth table of the function. You want to decide whether your input function is 0 on all x, so this constant 0 function, or otherwise is anything else. So there exists a x such that f of x is equal to 1. So you want to decide whether your input function f has this property or this property. And so we know that we can do this with Grover's algorithm. Although it's a little tricky, we didn't show the decision version, but it's close enough. You can convince yourself. Say you can combine with quantum counting. You can run the quantum counting and you know this, because here we don't know m. Okay. And anyway, so yeah, so we know that you can do this with square root n. No, m is everything, so there is no m. So we just said you can do this with square root n by running Grover's algorithm. But how do you prove that this other square root n is best possible? You can run any other algorithm. There might be many other different combination of gate you can run, and maybe some of them will use less queries to solve this search problem. And well, what we are going to show that is not possible. There is this omega square root n bound. Even if you try to design a different algorithm from Grover, it will not be better. At least in the symptomatic. Okay, and here's a reminder again. There are two functions, so it's a confusing part. So there is this small f, which is, you say it's a function, but it's actually input. Okay, so f is just, you can basically think it as an n-bit string. Although we also talk about its input, so there are two input and two functions. It's very annoying. Hopefully people are okay. But so this small f is a function with input from 0 to bigger minus 1. Okay? And we kind of think it's truth table as this big n-bit string. And there is another function you want to decide, which is a function on this big n-bit string. So here for decision version of search, the function is this, right? This yes and no is set here. And you can also see that this is just the OR function, right? OR of, I guess, if. Because we are just taking the OR of all those numbers. And if all of them are 0, then I guess we are reversing a yes and a no. Sorry, no. And yes. Right? So OR of everything 0 is 0, and OR of if there is some 1, then OR is 1. Okay? But Anyway, we don't really need to know it's an over function. It's just some digression here. We know we are solving the search function. Okay, so that's the lower bound, and now we go to the high-level idea of how do we do a lower bound. So first we write down what the query algorithm look like. Okay. So once again, the query algorithm look like this. This is a little, okay, we are a little lazy because we don't write and see that. Anyway, so you have some input, start with all 0, then you can do some unitary. That doesn't depend on your function. It can be very complicated because we don't care about computational complexity. And then you will do your oracle, then you do another very complicated unitary, and then you do your oracle, etc. And at the end, you will do some unitary, and you will do measurement here. Okay? So this is just a generic representation of a query algorithm. It doesn't say anything but that you run many query here. Right? So you have 1, 2, 3, and let's say it's called, and the number is kind of important, so we are doing k queries here. Okay, 2, 3k. Yeah, and so the way we are tracking how many queries we use is by tracking the distance between quantum state. Okay, so that's, I guess that's keeping this order. Okay, so let's make a definition here. So let's define when you run this algorithm. When you run to here, let's define this state as psi f0. Okay, and after then you run your OF, then another U1, then say this state is psi f1, etc. And at the end, your state will be psi fk. So we have this superscript f here. So this is the important part. We have this f here, right? So you see that the state it depends on your input string, and that makes sense, right? Because your oracle depends on this input string, this bigger input string. Okay. So different input string hopefully will give you different state. Okay. And now the idea is that we will track the distance between, so this distance between those states and between different input strings. Right? So we'll see how this number changes. So this different f and f prime. This is beta. Okay, let's draw the blue here. Okay. So we have f and f prime, and okay. So there are two things here, right? So the difference depends on what f and f prime you pick, and also depend on this t, right? And basically we want to see how this thing grow with t. So this means t is the number of steps here, right? So hoping that as t increase, this thing will increase, but not too fast. Okay, so let's keep doing this, and it doesn't, yeah, and okay, yeah. So let's say this one first. So the idea is that if you look at the starting state, you see this psi f0 thing. You haven't do any query yet, right? So this thing is actually same for every f because it just doesn't depend on f. So I guess we have a mental picture, right? Maybe this will help. We have a mental picture that you have a whole bunch of state, and your quantum state is something on a very high dimensional ball. But at the start, every psi f0 start here, right? You have lots of things here. And as you evolve through the algorithm, then things got split up, okay? Right? And hopefully they don't split up too fast. And so we'll prove that they don't split up too fast. So, and another thing is, so at the end you will do some measurements, so you kind of cut the ball in half, right? This is a very schematic, okay? And so we will do some measurement here, and now remember what we want to do. We want to do a decision problem. We want to say it's yes or no here, right? Yes, no. So we are having a very generic idea for every decision problem. So at the end, you want to see whether your problem is yes and no. And so when you do this couple in half thing, then you probably want whenever your f is something yes instance, then this part of the ball will be yes, and this part of the ball will be no, right? And then because you can distinguish them from yes and no, and so the state here and the state here are probably very far away. Okay. So they start with no distance, and they need to end with very far away. Okay. So and then we'll have a lower bound on every query. So every of these steps cannot increase the distance too much, and then you can just do basic arithmetic. So you need to travel this distance, but each step is small, then you need to run many steps. Okay, so that's the idea. And let's see this is a high level idea. Then let's see the idea in more detail. And as we say, we want to track this distance between states. And the distance we use here is kind of funny. But anyway, is you just take those two vectors and take their difference and do square. But it doesn't actually matter because you can say you actually take inner product. Then if you take inner product, then the inner product will drop from 1 to 0. And this is from 0 to 1. So it doesn't really matter. Anyway, and as we said, everything starts with the same point because at the starting point, just nothing depends on f. So all the starting things should be the same. Okay? And then we are separating things into yes and no, right? And so now consider your FF prime pair. So if your FF prime pair have different yes and no, so big F of F doesn't equal to big F of F prime, then at the end of the algorithm, there should be one of them should be projected to yes, one of them should be projected to no, then they should be pretty far away. Okay? Okay. And I guess we didn't, we'll have a more rigorous proof here. But hopefully this may intuitively make sense. Say the end you do, I don't know. This is a bit tricky, but yeah, hopefully it makes sense now. You want to do some measurement to separate them, then intuitively they should be pretty far away, and this will be, we'll see this in a lot of different ways at the end of this slide. Okay. But anyway, if you want the constant probability, constant probability to differentiate them, then you can feel that it's pretty normal to have this distance to be also some constant number, right? And now we're mixing this with our search problem. or function. So in a search problem, so maybe this f is a no input, where there is only one no input for the search problem. That's the O0 bit string. And f prime can be really anything else, but we'll actually focusing on those f prime that things pretty hard to distinguish from this f. So if you want to stay very close to this thing, but still have a 1 somewhere, then just have 1 somewhere. Right? So yeah, so that's f prime is a string that has a unique x such that f of x equal to 1. So it's a string that's 0 everywhere, but at this x place, you have a 1. Okay. Okay. And then we're going to show why is this thing useful. So a very useful thing is that if you track this kind of thing, right? So we want to track how many OF we use. So this U that doesn't define F, better not do anything to our distance. Okay? And that is indeed true. Because now you think about if you have some state A and some state B. So A and B is this, because we just use a simpler notation. And you apply the same unitary on them, then this distance don't really change. Okay? Framework here is this. Right? This is what makes everything work, because our distance doesn't depend on those unitary that don't contain any query, and you can just do a calculation. You see what's the distance of UA minus UB, and you expand out things, then you find out that you have U dagger U equal to identity. And so we're just saying unitary preserve the distance of a state, or the non-square of a state. And really this is saying as the distance of A minus B. Okay? So all those unitary doesn't increase this distance. And then you know that all this distance increasing thing must come from you doing the oracles. Okay? So if you want to make psi f and psi f prime further from each other, then you need to use this OF or OF prime. Okay? Okay? This is the core part. And then now the question is how many of those we need to use to separate them, right? Because this thing is good on high level, but we want to get a little more detail. And okay, so how many of those we need to use? So remember, we are calculating this thing, and yeah, and so we know the start and end is like, well, on average is a constant, right? So oh no, we are talking about one pair, right? So let's say we just have a pair of f and f prime, right? So, and once again, f and f, a pair of f and f prime such that big F of f doesn't equal to big F of f prime. So just write it here. Big F of f doesn't equal to big F of f prime. And okay, if we just track one pair, then how many of those queries do we need to use to separate them? The answer is pretty bad. Actually, you only need one query, right? This is because, well, big F of f doesn't equal to big F of f prime. So f doesn't equal to f prime, right? So there must exist some x such that they are different. Okay? and they're different, and without this originality, let's say f. So let's say the location is x bar, and let's say we are doing search, so f is O0 and f bar has a 1 on it. Okay, sorry, f prime has a 1 on it, and then you can just run this thing, right? So maybe you just run it at the first place. So you use your U to rotate the state here to become x bar. Then you run OF and OF prime. Then you see that the result of OF and OF prime are very different because OF give you 0 and OF prime give you this 1, which give you a -1 factor. Right? And so that will separate the state a lot. And that will be bad, right? Because we want to use many steps to separate them. And so I guess we are out of time, so we'll see how we do that next class. Yeah. But a little spoiler, we do that by consider many pairs at once. Yeah. So all those different f prime. Yeah. Okay. Yeah, we're out of time, so see you on Thursday. And let's finish this technical. Question? No.